Hello, welcome to chemistry class. Today's class I'm going to explain about incongruent melting point systems. Incongruent melting point systems. The phase rule, we have studied the phase rule of the heterogeneous systems. It was proposed by Willard Gibbs in 1874. Here we have discussed about the phase. A phase is any part of a system which is homogeneously physically distinct by boundary phase and mechanically separable from other homogeneous parts of the system is called as phase. And example, water plus petrol, water per benzene, CCl4 plus water. There you have two phases. Next, ice, water, water vapor. We are having three phases. For example, ammonium chloride system you take, the phases are two, ammonia and HCl. So in the ice, water, water vapor, you have solid, liquid, gaseous phase. The phases are three. So these are the phases. So I'm explaining you the terms that are involved in the system. First, after understanding about the terms, we'll go on for the complete system. What are the component? It is denoted by C. Number of components in a system is the smallest number of independently variable constituents by means of which composition of every possible phase in the phase can be expressed with a formula. For example, in water system you have three phases, but the component is only one, H2O. Similarly, for the sulfur system you have four phases, but the component is only one. So component, it is denoted by C, and the chemical formulas involved in a system is components. Now, what is the term freedom? Degrees of freedom, denoted by F. The degrees of freedom of a system is number of factors, namely temperature, pressure, concentration of the components, which may be varied without altering the number of phases present in the equilibrium. It's called degrees of freedom. Example, pressure, temperature, concentration are the components which can be varied with the number of phases. Is a degrees of freedom. Now, what is Gibbs phase rule? So after giving this introduction, we'll go into the incongruent melting point system. The sum of the number of degrees of freedom, F, and number of phases P exceeds the number of components by 2 is called Gibbs phase rule. F plus P is equal to C plus 2. That is a Gibbs phase rule. F is equal to C minus P plus 2. C minus P plus 2. Now, one component system, you have water system as an example. Now coming to the two component system, the components are two. The chemical formulas you can see two. That is two component system. In the two component system, we have condensed system, reduced phase condensed system, reduced phase equation for the condensed system. The gaseous systems which involve large change of volume affected by pressure. But the systems having only solid and liquid phases are sufficiently affected by change of pressure, such as solid liquid systems with the gas phase is absent. So if a gas phase is absent, then that is condensate system. The degree of freedom in this system is reduced by 1. Here the vapor pressure is absent. For the solid, there is no vapor pressure. It is very less. Therefore, for the solid systems, the freedom decrease of freedom is reduced by 1. So therefore, you get the condensate system. Phase rule is changed, reduced phase rule you get. F prime is equal to C minus P plus 1. F prime is the number of degrees of freedom and C is the number of components, P is the phases. Now we'll see the reduced phase rule for the solid systems. When two solids are melted together and liquid is cooled, substances are deposited together. This is usually the case when the substances are isomorphous. The solid thus deposited is called solid solution. A solid solution is defined as homogeneous mixture of two or more crystalline solids in varying proportions. Now, the solid liquid equilibria we'll see. Solid liquid equilibria, it is divided into different types depending on miscibility of the two compounds in molten state. The two components are completely miscible is one type of equilibrium. The two components are partially miscible is the second solid liquid equilibrium. And the third one is the solid liquid components are immiscible. That is the third type of solid liquid equilibrium. Two components immiscible. Two components completely miscible. Two components partially miscible. Two components immiscible. Based on the nature of the solid phases that are separating during cooling the system of the type, it is divided into three types. As previously discussed, two components do not react. Two components do not form any compound, and on solidification they simply form a intimate mixture known as eutectic. Example, silver lead system was discussed. And the second type of system is the two components combine to form compound with congruent melting point. That is, two components form solid compound, intermetallic compound. It is stable up to its melting point. And the example was magnesium zinc system discussed in the previous class. Now, the third one is the two compounds combine to form compounds with incongruent melting point. Incongruent melting point. That is, two compounds form a solid compound which decomposes before reaching its melting point. The one which doesn't decompose but liquefies and stable to its melting point is congruent melting system. If two components form a intermetallic compound, but that solid compound on liquefaction it gets decomposed, it is unstable before reaching its melting point. Such a system is incongruent melting point system. Example, sodium chloride and water system. Salt and water form solid hydrate. There are several systems. Yeah, this is all the introduction given, which I'm giving for you before starting the incongruent melting point system. So phase rule, what is a phase? What is a component? What are the degrees of freedom? What is Gibbs phase rule? What is the reduced Gibbs phase rule? And what is one component system? What is two component system? And in the two component system, you have two compounds on reaction, you get an intimate, they don't react, but you get an intermediate intimate mixture, you get mixture. That is one type, A type. Now, the B type of two component system is two components they react and they form intermetallic compound, which is stable till its melting point. That is congruent melting system, B type. Yeah, B example. Now coming to the C, incongruent melting point system. Incongruent melting point system is the two compounds mix. The two compounds mix and they form intermetallic compound, which is unstable. It doesn't possess congruent melting point. It is unstable. It doesn't possess congruent melting system. It possesses incongruent melting point system. It gets decomposed. It gets decomposed before reaching its liquid state. Before melting itself, it gets decomposed. A system, a compound is said to possess incongruent melting point if on heating it decomposes, which has instability below its melting point and forms a new solid phase under solution having different composition from the corresponding solid state. It has no sharp melting point. The decomposition of its temperature is known as transition or meritectic or peritectic reaction, and the temperature, the incongruent melting point, is known as transition or meritectic or peritectic temperature. The decomposition of this temperature is transition, and it is meritectic or the peritectic reaction. And the temperature is transition temperature or meritectic temperature or peritectic temperature. You can see organic solvent, it gives new solid. Organic solid gives new solid plus solution melt. So following, I have given you here the examples of the binary systems which possess incongruent melting points. Gold, antimony system, solid bismuth system, solid potassium system, solid sulfate, sodium sulfate. Here, I'm repeating, gold, antimony system. The solid systems are gold, antimony system, sodium bismuth system, sodium potassium system, sodium sulfate water system, potassium chloride, and copper chloride system. Now today's class, I'm going to explain you about sodium potassium system. Now, this system, it is having incongruent melting system. Sodium potassium system with water. Yeah, we'll see. The compound which undergoes decomposition by formation of another solid is called incongruent melting system. There are many systems in which Compounds formed by combination of two components decomposes when heated, giving new solid phase and a solution, that's a liquid of a solid with different composition from that of compound. Such compounds are having incongruent melting. There are some systems where the compounds they form by combination of two components, but they get decomposed on heating and they give a new solid phase and this liquid. The solid with different composition. The composition is changing. For congruent, the composition doesn't change. For incongruent, the composition is changing. Such compounds are called as the incongruent melting points. So this temperature is transition or meritectic or peritectic reaction, and the temperatures are transition temperature or meritectic temperature or peritectic temperature. The two components combine to form a solid compound with incongruent melting point in which decomposes before reaching to its melting point. Decomposes before reaching the melting point. Example I have told you here. Sodium potassium system. Take. Here for incongruent melting point system, we can even take NaCl and water system. This is two component system. It is having incongruent melting point. The melting points of the sodium and potassium are 97.8 degrees centigrade, 63.8 degrees centigrade. These are shown in the phase diagram in the below figure. Both the elements chemically combine. Both the elements chemically combine together in the ratio of 2:1 to form compound Na2K. This compound is unstable. It decomposes into solid Na, melt at a temperature of 70 degrees centigrade. It is the incongruent melting point or peritectic temperature of the system. This system consists of four phases: solid potassium, solid sodium, solid Na2K, liquid Na and K. Okay, these are the four phases: solid K, solid sodium, solid Na2K, liquid Na2K, Na and K. Here you can see a clear cut phase diagram. X-axis, y-axis. X-axis we have taken composition and y-axis temperature. Now, here you can see the diagram. You can see the curves. Basing on the curves, basing on the eutectic points, congruent melting points, we can explain clearly about the total phase diagram, basing on the curves, areas, and points depicted. Next, here. As the pressure does not affect on this one equilibrium, degrees of freedom for the system is reduced by 1, reduced phase rule. It is applicable for the sodium potassium system. F prime is equal to C minus P plus 1. So the curves involved are AC curve, CD curve, CD curve, areas ACDB, ACDB are the curves. Next, area ACF, area ACF, ACF area. Now, area ECG, BDH, ECG, ECG, this one, ECG, and area BDH. This is one area, this is the second area, and this is the third area. And area FCG and IHLK, FCG, FCG is complete word. Area FCG and IK or is IHLK. IKLH. This is one area, this is second area. So 1, 2, 3, 4, 5 areas. Curves, AC curve, CD curve. Okay, these are the curves, and this is ACL, ECG, and BDH, IHLK, FCG. Now we'll see how the phase rule can be applied for these areas. Thereon, we'll see about the eutectic points, and after the eutectic points, we'll see about the curves, ACBD, ACDB, and ACF curves. ACBD and CD. First CD curve, fusion curve of Na2K. CD curve, fusion curve of the solid, this one. This is the freezing curve, AC curve. AC. Then CD curve. So AC curve is the fusion curve of the potassium. Potassium is getting fused here. Combination is liquid plus equipment plus potassium. This curve shows lowering in freezing point of potassium by addition of sodium, and it continues till the point C is reached. This curve shows lowering freezing point of potassium by addition of sodium. So as you add sodium, potassium is getting freezed. It is continuing all through the curve till C. Along this curve, potassium K separates out as a solid. It's a solid phase. And another new phase, Na2K, is also getting separated at point C. Na2K is also getting separated. So you're getting solid K and solid Na2K. The two phases exist in equilibrium. Solid K and solid Na2K. F is equal to C minus P plus 1. This is equal to 2 minus 2 plus 1. Hence the system is univariant along this curve. Now, along CD curve, fusion curve of Na2K. Along this curve, the two phases exist in equilibrium. The Na2K is stable along this curve. If further the compound would be stable as having congruent melting points, then the curve may be plotted up to melting point E of the compound. See, along this curve, two phases exist in equilibrium. That is, Na2K is stable along this curve. Further, if compound is stable having congruent melting point, curve would have been plotted up to melting point E of the compound. But it is not stable. Here, CD. For this CD, Na2K is getting separated. Still continues if it's a congruent point, then we could have been stable Na2K along this curve. So Na2Ks is in equilibrium with liquid. Phases are 2. Na2K. Here Na2K, it is in equilibrium with liquid. Here the P is 2, the phases are 2, solid and liquid. C is 2. You are having Na and K. So C is 2. What is the formula? F is equal to C minus P plus 1. This is equal to minus 3 plus 1 equal to 0. So it is invariant. The system is invariant at point D. The system is invariant at point D. Okay, along this curve, P is equal to 2, C is equal to 2. So 2 minus 2 plus 1, it is univariant. Univariant, C and P. Now, going to the point D, you are having 3 phases. Here at this point 3, you are having 3 phases. So in this 3 phases, P is 3. At point D, P is 3, C is 2. So F is equal to 2 minus 3 plus 1. 3 minus 3, 0. So at point D, it is invariant system. Along AC and CD, it is univariant. 2 minus 2 plus 1 is equal to 1 along AC and along CD. Now coming to the areas. In the areas ACDB, area ACDB, it contains only one liquid phase, that is melt of sodium, potassium and Na2K. So that intermetallic compound, sodium and potassium, complete melt, ACDB. ACDB, it's complete melt. P is 1, C is 2. So F is equal to C is 2, P is 1. 2 minus 1 plus 1. 2 minus 1 here, plus 1. It is 2. Bivariant system. For the area ACDB, it is bivariant system. Now for area ACF, ECG. For area ACF and area ACG, will see. Here ACF and ACG will see. It consists of two phases, solid K. ACF, it consists of two phases, solid K and liquid. ACF, two phases, solid K and liquid. Solid K and liquid in this area. And area ECG consists of two phases, solid Na2K and liquid. ECG area, two phases. ECG, two phases, solid Na2K and liquid melt. C is to P is to ECG. Similarly, for area BDH. Similarly, for area BDH, it consists of two phases, solid sodium and liquid. BDH, solid sodium and liquid. So C is 2 and even P is 2. Okay, C is 2 and P is 2 univariate. For all the areas you get univariate. Only for one area you get bivariate. And for the points you get invariant. For the curves you get univariate. Yeah. Next we'll see, look onto the another area below FCG. Area below FCG. Solid K and solid Na2K. FCG, solid K and solid Na2K. So solid can, here FCG, solid can, solid Na. C is 2, here C is 2, P is 1. Only one phase, solid phase. You get bivariant system. Similarly, IHLK, P is 2, C is 2, you get univariant. See, here also for FCG, you get P is 1, C is 2, only one phase, FCG, below FCG. FCG, F, it's a solid one. So you get P is 1, you get P is, sorry, the P is 2, you get C is 2. Molten and solid. So for these, P is 2 and C is 2, a reduced phase rule. So univariant system. Now, this is very clear for you about the areas. In this one, along the curves, we are getting univariant AC, CD. And at point C, you take tick point, and incongruent melting point D, 70 degrees, we get invariant systems. And in the areas here, 1, 2, 3, 5. So 1, 2, 3, 4, 5. These 5 areas, you get univariant system. So P is equal to 2, C is equal to 2. You get univariant system. Now, only one area it is special, just like eutectic system and congruent system. Even for the incongruent system, you have the same ACDB area, above this area. ACDB above this area, you have only one phase, two components. Two components and one phase. So you get bivariant system. For that one, you get bivariant system, ACDB. Yeah, the salient features can be discussed here. The complete one, as I've shown you the diagram, explained for sodium, potassium system, incongruent melting system. The compound formed is unstable, and on melting, you don't get the same composition. So therefore, a different compound is formed. Solid melt, a different one is formed. So it is incongruent melting system. Transition reaction. The transition takes place. A new compound is formed, giving a new solid. So these we have discussed. See, Everything I have told you about the curves. The curves, it is univariate system for points, eutectic point D, congruent melting system, eutectic point C, and congruent melting point D. It is invariant. And for the areas 1, 2, here 3, this 4, and this 5, for these areas you get univariate. Everything is in univariate except of the points, eutectic point and congruent systems. And coming to the area, only one area you get bivariant system. I hope you have understood the diagram. See here, the curves univariant, points invariant, areas univariant, everything is invariant. Curves, areas, univariant. Only the points you have invariant. And only at one point you have bivariant, that is this one, above curve. You have understood, I hope. Now we'll see the table, salient features completely in a table. Curve AC freezing curve of K. You have potassium and the melt with two phases, univariate. We have curve BD, that is the freezing curve of the sodium. Freezing curve of the sodium. BD. There the sodium and the melt is there containing two phases. System, you can see it is univariate. Curve CD, you have two phases, sodium, potassium and melt. It is having two phases, univariate. The phases only change, the components are two everywhere. So in a table, it's not given clearly about the components. Because it's a two component system, you have to. And coming to the areas, your curve CD also you have phases 2. And coming to the areas ACDB, area ACDB, bivariant system. Only this area, it's a different one because the phases are only one. C is again 2 and bivariant system. Now let us see the area of ACF. ACF, their potassium and the melt. Again, phases 2, univariate. Now area BDH. So area BDH, sodium and the melt, containing sodium and intermetallic compound. Phases are 2 and univariate. Area CDIG, NaK melt, is containing potassium and sodium potassium. Univariant system you get. Area below FGC, sodium, potassium and potassium, both of them are the solids. You get two phases and it's univariant system. Area below line IH, sodium, potassium and sodium, both of them are solids. Phases are two, univariant. The point C eutectic, you get three phases, invariant system. The C is 2 and another eutectic point, that is I. Yeah, two eutectic points, C and I. D is the incongruent melting point. And for I also you are having three phases, two components, three phases and two components. Invariant system at I. For eutectic points, it is P is 3, C is 2, invariant system. And similarly for D also. Now this is a complete explanation for incongruent melting system, taking the example of sodium potassium. The same can be explained for sodium chloride and water system also. What are the applications for this phase rule? It has wide applications in electronic industries, pharmaceutical science, medical sciences, and the major applications you can see here: shoulders, shouldering, safety plug. Here, these are the ones. Shoulder is an alloy. You keep doing shouldering. Homogeneous mixture having melting point lower than metal pieces. So shoulders, it's an alloy having it's a homogeneous mixture, less melting point. I have melting point lower than that of metal. You can join either using this one. This soldering have composition somewhat different from the eutectics. So the freezing occurs over the range of temperatures. And the quality of the shoulder depends upon the formation of the surface alloy between the shoulder and the parts of the metal that is used. So shoulder alloy, it's based upon the melting point designed depending on the metals that you join. So there are many essential qualities. Softer shoulder, you get by lead and tin. Plumber alloy, you get lead 67% and tin 33%. Half alloy, you get lead 50%, tin 50%. So generally half alloy is mostly used, 50% lead, 50% tin for shouldering, and it's a bit expensive one, and due to high contents of tin, this is not used widely for the electrical appliances. It contains 60% of the lead and used in the electrical wires. Even for the safety plug, we can use it. Safety plugs are also known as the safety fuses. It is an alloy having low melting point, safe working and avoid accidents, safety plug. And safety fuses are used in buildings to protect them against fires. So one alloy, it's woods metal. It's used in safety plugs. Bismuth 50%, lead 25%, tin 2.5%, cadmium 12.5%. So these are the ones alloys used in the safety plug. So these are the applications for the phase rule. So since previous 3 sessions, I'm discussing you about the phase rule. What are the terms involved? What is the rule? Phase, degrees of freedom, components, Gibbs phase rule, reduced phase rule, and one component system, two component system, into again eutectic system, congruent system, and incongruent system is discussed. I hope everybody have understood my lecture. Thank you for listening to my lecture. Thank you, everybody.